Hey kids, so pardon me. Let's go through this unit a little bit. Slideshow. All right. Here I am in the room, by the way. I'm in the classroom. My son's lesson was not a mile away. Thank you, Apple Maps. It was 20 miles away. So anyway, all right. So what we learned this unit is that reactions occur because of collisions. And one of the first things we did was we took some Alka-Seltzer tablet and we took a little bit of the stuff that's in Alka-Seltzer tablets and we mixed them both with acid, and we saw that the Alka-Seltzer tablet took longer to start bubbling than the ground up stuff. And that's because in order for a reaction to occur, the things need to collide into each other, the atoms or the molecules or the formula units or whatever it is. So that is described here, basically, where here's like chlorine and here's some other thing that's trying to react with chlorine. Let's call it sodium. All right, so if then you increase the temperature, things will move around a lot faster, and when they're moving around a lot faster, they'll collide more often. If you decrease the temperature, you can slow things down and they won't run into each other as often. Concentration, so if you increase the number of atoms in here or molecules or whatever it is, then more things will collide, right? Because there's just less room. Go to New York sometime or Disney World. If you decrease the concentration, then you will have things less jumbled up together, let's use that term, and therefore they won't run into each other as often. And then surface area, if you expose more of either a reactant, then there's more area for it to collide. It's something I told someone today. If you remember in Star Wars, one of the first ones where they're trying to shoot the actual first one, where they try to shoot the torpedo down a little hole. If the hole's bigger, then they can do it more easily, right? So the greater the surface area, the easier it is for something to react, maybe. All right, so then we talked about driving forces. Reactions can go either way. Is this really? Yeah, that is the first one. All right, so reactions can go either way. And one way to make sure that they go toward product is if you form a gas, or you form a precipitate or a solid, or you form a non-electrolyte like water. And that'll all make reactions tend to move toward the products rather than sort of go back and forth. All right, I don't think we need to go over these, but very quickly, this means solid, liquid, gas. Aqueous means dissolved in water. This sign means that the reaction's going to the right. Heat is a triangle. Plus just means plus, and then reaction go either way, and you signify that. All right, so, excuse me. We had chili for dinner. It's not going to be good today, kids. All right, law of conservation of mass. Mass is neither created nor destroyed during ordinary chemical reactions or physical changes. That's Antoine Lavoisier who came up with that, and he's looking off into the distance there. Mass of the reactants, therefore, has to equal the mass of the products when you do chemistry. He disproved the existence that flames have mass, which is called phlogiston. Oh no, there's some outside, kids. All right, so here's a reaction where you have calcium chloride and sodium sulfate, and here they're not mixed, and you can see it weighs 323 grams, 300.23 grams. And then when you do mix them and stuff starts happening, it still weighs 300.23 grams, and that's because matter is neither created nor destroyed. And we got into things like, why would then, when you burn something, does it lose mass? And that's because you're losing chemicals to the atmosphere, right? Carbon dioxide and water or whatever else when you burn something, will sort of go up into smoke, literally, and that smoke goes away. And if you could capture that smoke and weigh it, it would weigh as much as everything together after would weigh as much as before. So when we balance chemical equations, you should know how to do this, right? For every atom you have as a reactant, you need it there as a product. So here there's 4 blue things, and here there's still 4 blue things, and here there are 12 white things, and here there are still 12 white things. So they change around, and we did this with the models, and you have to make sure that you know how to balance things and what that all means. So again, Again, you should know how to balance things. Take inventory of both sides. You only move coefficients. You do not deal with the subscripts. So here, CH4 going to CO2, you can't be like, hey, you know what? If this was H2O2, this would be a lot easier. Can't do that. You have to balance the numbers in front. So this would be, oh, you know what? There's a pen here. Anyway, should I get the pen? I'm not going to get the pen. I should. It's not in the drawer. All right, it's in my desk. It'll be all right. All right, so there's one carbon here, there's one carbon there. Oxygens go with that. You need 2 oxygens, one to make 4 oxygens, 2 O2s, 2 to make the CO2, and 2 to make the water. And that's what we did in class. All right. So these are some things. So again, we're looking to make products, and things will go in this direction if you have a driving force, like making water or making a gas or making a solid. I think that's a solid. All right. So then there's different types of reactions. Synthesis is one product from a multitude of atoms or chemicals or elements or whatever. And that would be, for example, if you have a bunch of baking things and you mix them all together and you make one cake. There was a bunch of stuff, and then you made one cake. So the cake weighs more than any one of the things, the flour, the sugar, the eggs. But actually, if you weighed up all that stuff and you weighed the cake, it should weigh the same when you're done, right? Hopefully. So synthesis, if you know what synthesis means, it means making one thing from a lot of things. Conveniently enough. All right. Classifying, we have decomposition, one reactant. So you have one thing breaking down into many things. And here's a log. And we talked about dead squirrels, that when a squirrel gets hit by a car, it starts to weigh less and less as more and more things from the squirrel go away, from ants or birds or fungus or whatever it is that's going to eat the squirrel. So when you have one thing and it's going into multiple things, that is decomposition. And then single replacement is when one usually element breaks up a compound so that the one element is now part of the compound and one of the elements in the compound is left out on their own. For example, here done by Mr. Philip Redkin, iron comes in and knocks copper off the sulfate, and then copper's by itself and iron has a sulfate. So here's the iron, it takes the sulfate away, and now copper's all by itself. All right, and then there's double displacement or double replacement. I keep saying the same, I keep mixing those up, but just know that I can say either one. Here's Daisy and Peach, or Peach and Daisy. Peach and Daisy, I think. All right, Mario and Luigi, and then Mario was with Luigi, now he's with Peach. Luigi was with Mario, now he's with Daisy. So that's double displacement. So they come in pairs and they leave in pairs, but they're not the same. So here you can see calcium leaving with nitrate, it came in with bromine, and silver leaving with bromine, it came in with nitrate. All right, and here's a nice thing here where the silver is taking the chloride from the potassium, and the potassium is taking the nitrate from the silver. Look at that. Thanks, Philip. All right, last one is combustion. And a combustion reaction, you make carbon dioxide and water from some hydrocarbon and oxygen, and this is how we burn things and get our fuel and whatnot. And that's that. Pretty much diatomic molecules. Remember, there are 7 that exist as diatomic molecules. I've had more driving forces. We don't need to talk about that. All right, exothermic and endothermic. This we did talk about. So reactions involve energy, and you need to either have energy released or absorbed. If it's released, we say it's exothermic. Exo meaning sort of leaving, and endo going into means it absorbed. So most chemical reactions are going to need a little push to get them going anyway, and we call that the activation energy. So even if something like burning carbon. Anyway, like the magnesium we did, or if you burn a piece of paper, right, you still need, or if you light a fuse, right, you still need to get things moving in a certain direction. So exothermic reactions, you'll have something like H2 and O2, which when you light them on fire, make this huge sonic boom. It's really cool. And they do that because they're forming water, which is a more stable product. And as these form that, they, even though you need a little activation energy, they're going downhill, they're decreasing in energy, so that's exothermic. Energy is being released from these to get down there. And the reactants are of higher energy. And the products, energy is like a product, right? So you get the water plus all this energy when an exothermic reaction happens. Now, the opposite of that is an endothermic reaction. And I did this. I took water and I hooked it up to a battery to make it H2 and O2. So for water to get all the way up to H2 and O2, you got to put energy in. So water is of lower energy than the H2O2. So to get up the hill, you got to put some energy in. And then you're going to have a large activation energy in this case. It takes a lot of energy to get up here. Products are generally higher than the reactants, and energy is like a reactant. You have to add energy to this to get up to that hill. All right. Talked a little bit about entropy. I didn't cover this in this test. It'll come back though. But entropy basically means it takes energy to make something ordered. And we talked a little bit about this, that the elements up here, and we did this with the switcheroos where we put copper. Where's copper? Copper, here it is, in with silver. So silver was in a silver nitrate, and we put a piece of copper in there, and the copper went into the solution, and the silver came out of the solution because silver is more stable than copper. Basically, copper would prefer to be in solution in the presence of silver. So we got a bunch of silver crystallizing on the copper wire, and then we saw the copper go into the solution and turn it a little bit blue. And then we did the zinc in acid, and we did the copper in acid. Nothing happened when copper didn't make H2, but zinc did make H2 when it was thrown in acid. And then we talked about what would happen, and some of you did it with magnesium if you put it in acid. So you just need to realize these like to keep their electrons, stay as metals. They have high electronegativities for metals, and they're pretty stable as is, and that's why we make jewelry with this stuff. And that these things are not stable, that you just throw these in water and they start a fire. So they will lose their electrons in a heartbeat to become ions, and they have very low electronegativities because of that. All right, we didn't really do that. We talked about that already. And like aluminum foil, if you ever noticed when you cook something acidic with aluminum foil, it'll all get kind of sticky and nasty because the acid is reacting with the aluminum. And that's a thing. All right, so we didn't really do much of this. Let's go back to dissolving. So we did do with double displacement. If you put a bunch of ions into water and some of them decide to get together and form a solid, we say that's a reaction. And the alternative to that is you put a bunch of things into water and then they just stay swimming in water. Nothing forms together to make a solid. So then we say there's no reaction. And we did some of this with the precipitates. Now, I originally thought this was a good chart, but it's not. I gave you a better chart. But basically, when you switch your partners, when calcium gets with sulfate and ammonium here gets with nitrate, you can look here. No nitrates are exceptions to being soluble. So that means anytime you see a nitrate, it's soluble. And sulfates are also soluble except for strontium, barium, mercury, and lead. So in this case, that would be calcium sulfate. So that would be no reaction of reading this. But you just know how to read the other thing that will be given to you, the crisscross one. All right, so that's some more. Wow, that's it. So that's all we did, I guess. All right, so is there anything else I wanted to tell you? Let me just show you real quick two things. Since I have your ear, you can stop listening now if you want to. But if you go to association of salt. All right, let me turn that off. So remember, as Simba said, or Mufasa. All right, salt has these pluses and chlorine minuses. So the pluses are sodium, and that water will go and pull those apart. So if the salt wants to stay together more than the water wants to pull it apart, then that's a reaction. So here you can see the positive hydrogens pulling away the negative chlorines. This is a better one. I should have shown this one. I just found this recently. And here you see the negative oxygens of water pulling away the positive sodiums. And if these things want to stay apart in water more than they want to come together, they dissolve and they're aqueous. And if they want to come together, then we say there's a reaction. And there's certain things that like to stay together more than they like to be pulled apart. And that was good. And then the other thing I wanted to show you real quick is the H2 hydrogen reaction bubbles. Let's try that. Where is that lady? There she is. All right, so this is fun. This happened where the guy was talking to this woman about doing things, but basically, here's the fun part. All right.
We're going to see what happens if we add a little energy to that from the flame of a match while they're in the palm of your hands. Alrighty. So what I want you to do here in just a second is scoop up as many of those bubbles as you can. Just skim them off the top. I'm getting nervous. Leave the water.
So these bubbles have hydrogen oxygen in them. Okay. And just to show you how good this reaction is.
And for everybody else in the studio, you might want to plug your ears because in 3, 2, 1. You okay? Yeah. You had a lot of bubbles there. That was and you know, the cool thing about that, you're okay, right? Show your hands. Okay, I'm alive. Okay, dry your hands off. The cool thing about that is that reaction happens so quickly, it actually creates a supersonic shockwave. Yeah. I felt it.
All right, so
I can feel it. Yeah, I think you blew me away. Okay.
Let's watch that in slow-mo.
Today from noon. Good, Carl. Thanks so much. I'll send it over to the guys, Sam Tech Sports.
All right, slow-mo, instant replay.
2, 1.
All right, I forgot to show you that, but that is what happens when you have hydrogen oxygen in water. All right, so hopefully that's something to help you study tonight. Oh, that's not what I meant to do. Here we go. Now